You do it all the time. You pop open a terminal, type a command, hit enter, and poof, magic. But what's really going on there? What's the elegant dance happening just under the surface of your command line? Well, in this explainer, we're going to pull back that curtain. Right, this probably looks pretty familiar. You're in your shell, you type something like ls to list files, or echo hello world, and the computer just does it. But here's the secret. Your shell isn't actually listing those files. It's more like the conductor of an orchestra. It doesn't play any instruments, it just tells the real programs what to do and when to do it. So what is that coordination? What happens in those few milliseconds between your finger hitting the Enter key and the output splashing onto your screen? How does your shell, just one single program, somehow conjure up a totally different program, let it run, and then gracefully take back control? That, right there, is the big mystery we're going to solve today.
Okay, so the whole journey starts with this one kind of weird idea, cloning. Before your computer can run a new program, it first has to make an exact, perfect copy of the program it's already running. In this case, your shell.
This is done with a system call called fork, and the whole parent-child analogy is perfect. The original process, your shell, becomes the parent. When it calls fork, it creates a brand new child process that is, for a split second, its identical twin. It's got the same code, the same memory, the whole shebang. And this visualizes it perfectly. Before the fork call, you've got one single process chugging along. Afterwards, boom, there are two. Both the parent and the child are now running the exact same code from the exact same point. The program's timeline has literally just forked in two.
This little phrase really captures the weird magic of fork. You call the function one time, but it somehow returns two times. How is that possible? Well, because after the split, it has to give a result back in both processes. In the parent, it returns the ID number of its new child, but in the child, it returns 0. And that simple difference is everything. It's how each process knows who it is. Am I the parent or am I the child?
Okay, so we've cloned our process. Great, but that immediately creates a new problem. We've got two processes running around now. So how does the parent keep tabs on the child? How do they sync up? Turns out there's a fundamental rule of process management. A parent has a responsibility to its child. It needs to hang around and see the child's job through to the end. Because if it doesn't, well, things get a little weird. And this is hands down one of my favorite quotes from the source material. I mean, come on, it sounds like something from a bad horror movie, but believe it or not, zombie children are very real and very important concept in computer systems. So a zombie process is basically a child that's finished its work, but its parent hasn't bothered to check in and acknowledge that it's done. So the process isn't running anymore. It's dead, but it's still taking up a slot in the system's main process table. So it's not truly gone either. It's just a zombie. And if you let too many of them pile up, they can actually clog the whole system. The tool for cleaning up or reaping these zombies is waitpid. The parent calls this function, and it basically just hits pause. The parent just waits around until the child process is officially finished, and once it is, waitpid cleans up that leftover zombie entry and lets the parent get back to work. It's the tidy, responsible thing to do. So we can clone a process, and we can wait for it. But making a perfect copy of the shell isn't really our goal, right? We want it to run a completely different command. And that brings us to the final and maybe coolest piece of the puzzle, the takeover. Yeah, this is the whole point. The child process starts life as a perfect clone of the shell. So how on earth does it transform itself from being a shell into being the ls command? It can't just stay a clone forever. The answer is a family of functions called exec, and we're looking at execvp. I absolutely love the word the source material uses for this. It cannibalizes the current process. When the child process calls execvp, its entire memory, its code, its whole identity, it's all completely wiped out and replaced by the new program we want to run. And if it works, the old code is gone forever. Execvp never, ever returns. Check out this code. The program sets up the arguments for ls-l, and then it calls execvp. Now look closely. The very next line is supposed to print an error message. But if you look at the output, there's no error message. That line of code was never even reached. The second execvp was called, the original program just vanished, totally replaced by ls. The takeover is complete.
So there we have it, our three magic ingredients. We have fork to clone, waitpid to coordinate, and execvp to transform. Let's put them all together and see how we can build a shell.
And honestly, it really is this simple. This three-step recipe is the beating heart of every single command line shell you have ever used. Step 1, the shell clones itself. Step 2, that new child process immediately transforms into the command you actually wanted to run. And step 3, the original shell, the parent, just coordinates. It waits patiently for that command to finish before it gives you a new prompt.
And here it is, right here in actual C code. You can see it clear as day. First, there's a call to fork. Then, you see that if statement, the one that only the child process can enter. Right inside there is the call to exec VP. And then, after that block, the parent makes the call to waitpid. It's our three-step recipe, right there on the screen.
Now there is one last, really clever little twist here. You'll notice the code doesn't actually call XVP on ls directly. It calls it on /bin/shell. Why? Well, because a command line isn't always just a program name. It can have pipes and redirects and all sorts of complex stuff. So instead of trying to figure all that out ourselves, we just let a shell do it. We tell our child process to become a brand new shell whose one and only job is to run that command string we gave it and then exit. It's a beautifully simple and powerful solution.
And once you really understand this fundamental fork, exec, wait pattern, you suddenly have the key to unlock almost every major feature of a modern, powerful shell.
Think about running a command in the background, when you stick that little ampersand at the end. The secret behind that incredibly useful feature is just ridiculously simple. For a normal foreground job, the parent shell waits. For a background job, it just doesn't. The parent forks, the child execs, and the parent completely skips the waitpid step and immediately asks you for the next command. That's it. A major feature, powered by simply not calling one single function.
So the next time you type a command and hit enter, you'll know. You'll know about the elegant little dance that's happening behind the scenes. A clone is born, it immediately transforms itself, and its parent waits patiently for it to finish its job. It's the foundation for so much of what makes our computers so powerful. And it kind of makes you wonder, doesn't it? What other simple, powerful secrets are hiding in plain sight?